In our previous video, we talked about some properties of sound waves. Frequency, wavelength, and time period are some of those properties that we discussed. We ended the video by saying that there is some relation between the frequency and time period of a sound wave. Let us find that relation. We have seen this graph previously. It represents the propagation of sound wave in a medium. Sound propagates through a medium in the form of high-pressure regions called compressions and low-pressure regions called rarefactions. Let's say the time period of a sound wave is 0.5 seconds. What does it mean? It means that the time required for a sound wave to complete one oscillation is 0.5 seconds. How many oscillations will be completed in 1 second? It's simple logic. If it takes 0.5 seconds, that is half a second, to complete one oscillation, then 2 oscillations will be completed in 1 second. And this is nothing but the frequency of a sound wave. Remember that the frequency is the number of oscillations per unit time. Here we are measuring time in seconds. So the frequency will be number of oscillations per second. And here we get 2 oscillations per second, which is nothing but 2 Hertz. Hertz is the SI unit of frequency. Now let me ask you another question. If the time required for one oscillation is 0.25 seconds, then how many oscillations will be completed in 1 second? Yes, now the frequency will be 4 Hertz. As it completes one oscillation in 0.25 seconds, it will complete 4 oscillations in 1 second. But did you notice something in these 2 examples? How are we getting these values? If you see, we are simply taking the reciprocal of time period to get the frequency. In the first example, 1 over 0.5 will give us 2. In the second example, 1 over 0.25 will give us 4. So if the time required for one oscillation is t, then the frequency will be 1 over t. That's the relation between frequency and the time period of a sound wave. Frequency is equal to the reciprocal of time period. Frequency is generally notated with the Greek symbol nu. We can write this as nu is equal to 1 over t. I hope that you've understood the relation now. We didn't have to memorize the formula, we derived it. Let us move on to a new concept which is connected to this one. Say both a guitar and a flute are played at the same time in an orchestra. The sounds coming from both of them travel through air with the same speed. The medium through which the sound travels as well as the speed is the same. Then why is it that we hear different sounds? Why does the sound from the flute differ from that of the guitar? It's because of one of the characteristics of sound. Do you know which characteristic I'm talking about? It's called pitch. As we've seen before, pitch is the perceptual property of sound. It is determined by the frequency of source. More the frequency, higher will be the pitch. To know if you've really understood what pitch means, here are 2 graphs for you. These are graphs of 2 different sound waves. Which sound among these 2 do you think will have higher pitch? We can clearly see that the frequency of the second sound wave is much higher. More oscillations are happening per second relative to the first one. Hence, the pitch of the second sound wave will be higher than the first one. Now that you've understood the concept of pitch, let us talk about the amplitude of a sound wave now. We know regions of peak compressions and rarefactions. These are those regions. This distance from the mean position to the maximum compression or rarefaction is called amplitude of a sound wave. This distance is the amplitude. If you strike the tuning fork gently on the rubber pad, you will hear some sound. But if you strike it harder, will there be any difference in the level of the sound that you hear? Yes, the sound will be louder. Why? It's because the source is vibrating with larger amplitude. Yes, the amplitude of source defines the loudness of sound. More the amplitude of sound, more will be its loudness. Since the source vibrates with larger amplitude, it means that the particles of the medium will also vibrate with larger amplitude. Here, these two figures show the amplitude of sound wave in both the cases. The one in which we strike tuning fork gently and the other in which we strike it fiercely. We see that the amplitude of wave is more in the second case. In the next video, we are going to discuss the speed of a sound wave and the wave equation. See you there.